Hello, we are Group 45 and our project is Autodesk Inventor Predictive Analytics. As a team, we want to develop a system that can predict a user's next command based on their previous inputs. This will improve workflow and a user's frustration with trying to find one command out of 3,800 available on Autodesk Inventor. Our system is intended to have a base amount of information learned, but once deployed, will continue to learn from the individual user. Our project has three main parts to it. The first is the predictive model, the second is integration with Inventor, and finally, the two applications will need to communicate in order to make the predictions and have them displayed to the user. For our predictive model, we have honed in on recurrent neural networks. These are neural networks that operate with a sort of memory. This will be helpful in our problem because we want to predict commands based off of previous inputs. This is an illustration of a recurrent neural network. It has input X, internal state S, and output O. The unfolded version depicts how the internal state is updated based on the previous state as well as the current input. When we were deciding to use a recurrent neural network, we primarily decided to use it based on its structure and how it has certain memory. They are also extremely popular and widely studied. At the same time, vanilla RNNs are not put to use on actual projects. They have a limitation associated with the way information is learned. The backpropagation through time has a fatal flaw. The RNN on the left has one hidden layer, while the one on the right has three hidden layers. It may seem like more hidden layers will allow the network to perform better. However, it turns out that including more hidden layers doesn't actually improve the accuracy and in many cases can reduce it. We randomly initialize the weight and biases in the network. When a problem occurs with the gradient being too small, the change made on the weights are near zero. This problem plagues the first few hidden layers, which means the later layers get trash information. The opposite problem can occur where the changes pushed through the RNN are too large and explode, causing the information to once again become garbage. It turns out that the gradient in deep neural networks is unstable, tending to either explode or vanish in earlier layers. A fix to the vanishing gradient problem is using long short-term memory networks, usually just called LSTMs. They are a special kind of recurrent neural network capable of learning long-term dependencies. LSTMs are explicitly designed to avoid the long-term dependency problem. The key to LSTMs is the cell state, the horizontal line running through the top of the diagram. The LSTM does have the ability to remove or add information to the cell state, carefully regulated by structures called gates. Gates are a way to optionally let information through. They are composed out of a sigmoid neural net layer and a pointwise multiplication operation. The sigmoid layer outputs numbers between 0 and 1, describing how much of each component should be let through. A value of 0 means let nothing through, while a value of 1 means let everything through. The three gates are the forget gate, the input gate, and the output gate. The first step in our LSTM is to decide what information we're going to throw away from the cell state. This decision is made by a sigmoid layer called the forget gate layer. It looks at the last output and current input and outputs a number between 0 and 1 for each number in the previous cell state. A 1 represents completely keep this, while a 0 represents completely get rid of this. The next step is to decide what new information we're going to store in the cell state. This has two parts. First, a sigmoid layer called the input gate layer decides which values will update. Next, a tanh layer creates a vector of new candidate values that could be added to the state. We'll combine these two to create an update to the state. We can now update the old cell state. We multiply the old state by the numbers we came up with through the forget gate, forgetting the things we decided we weren't worth keeping anymore in internal memory. Then we add the new candidate values scaled by how much we decided to update each state value. This output will be based on our cell state, but it'll be a filtered version. First, we run a sigmoid layer which decides what parts of the cell state we're going to output. Then we put the cell state through tanh to push the values to be between -1 and 1. And we multiply it by the output of the sigmoid gate. so that we only output the parts we decided to. In short, LSTM is a popular flavor of neural networks that has memory. It is frequently used for natural language processing problems, which we have expanded to our command prediction problem. Being so popular, all of the popular machine learning libraries support this architecture and have easy-to-use functions already predefined. For our implementation, we are required to develop a prototype or proof of concept. We want to show that there is merit in attempting to predict user commands. This being the case, our project is fine to have dependencies separate from Windows and Autodesk Inventor. We have therefore decided to make use of TensorFlow. TensorFlow has LSTM cells ready for us to use, and it will also handle the backpropagation through time. It also has some other optimization tools. We have also decided to use a 2-layer LSTM. It appears to train faster and can support more individual commands. Here's a snippet of code that we are currently using. We have a function which defines the RNN that we are currently using in our model. It takes in a row vector with columns equal to a hyperparameter we have set. Commands or words are made into numbers so that we can feed their values into the RNN. As you can see, TensorFlow makes it very easy to define a 2-layer LSTM because it has the structures already within its library. Here are further examples of TensorFlow at work. We have a cost function that is calculated using the cost entropy or log loss. And at the same time, we can also test how accurate our system is at any given point during training. To train our system, we have recently been provided with user data that has been collected by Autodesk. The entire data collection can contain a lot of information. However, the most important columns available to us have been listed. While discussing the limitations of the data, one question arose, which was, how should we account for pauses in command input? For instance, should we end a sequence of commands if a user is stagnant for over 15 seconds? Upon further reflection, we decided that although there was a pause, the command that eventually followed the pause was always going to occur. Our machines essentially understand times as action already. With this being the case, we have timestamps merely for order of commands entered. Session ID is another way we can extrapolate order. To speak to the data as a whole, it is not perfect. The longest set we have received tops out at 8,000 commands. This is a very small set. We would like hundreds of thousands of commands. One fix to this problem could be creating a set where user is not a column. This set is in the millions of commands, but the difference in user usage may be a detriment to predictive ability. Another issue with the data is many of the commands entered are navigation commands or undo and redo. These commands can appear randomly at any point during a user's work period. Ideally, these would be removed while gathering the data. However, it appears that we will need to develop a system that does it for us. The data isn't perfect, but we should be able to make use of it. For optimizing our system, there are a couple of strategies that we will employ in future iterations. The first will be to split the data into even pieces, for example, maybe 10 sets. We will then create multiple models. Each model will learn from 9 of the 10 sets, rotating which set they do not learn on. Then we will treat each set as a training set and have each model make a prediction. Then, as a best guess, we will have the average answer among the models be presented to the user. Another optimization involves messing with the hyperparameters of multiple models and changing which softmax function they make use of.
Now let's discuss the workflow of the add-in. The add-in will work in 3 primary stages: command gathering, inter-process communication, and displaying the result to the end user. The add-in observes commands entered by the user and stores the 5 most recently used commands in a queue. Then the commands are shipped through a piping protocol to the predictive model. The predictive model will read the sequence and return a predicted command. The command will then be displayed and usable to the user's discretion.
A necessary part of this project was identifying a means to pass data between the add-in and the predictive model. In our research, we came up with 2 viable solutions: sockets and pipes. Ultimately, pipes were chosen over sockets because sockets have a number of features which are unnecessary to our project. Namely, that sockets require that the data is packetized and sent through the network protocols. Pipes avoid this issue and are able to achieve much the same outcome with minimal overhead. In order to prevent slowdowns, we have opted for a multi-threaded approach. Each application will consist of a minimum of 3 threads: the main application thread, a read thread, and a write thread. This structure will allow each process to send and receive data without interfering with the operations of the main application.